Imagine a scientist is on the verge of a breakthrough, but the key evidence is trapped inside a blurry, hazy image from their microscope. This isn't a rare problem. The best confocal microscopes that produce stunningly sharp images are incredibly expensive, while more accessible wide-field microscopes often yield hazy results due to out-of-focus light. For years, AI developers have tried to fix this with computational dehazing, but they always hit a wall: the perception distortion trade-off. This means AI models could either be super accurate to the original data but look artificial, high fidelity, or they could generate beautiful, realistic-looking images that might invent details that weren't there, high realism. You could have accuracy or beauty, but not both. This paper introduces a new method called haze matching that finally finds the sweet spot. The researchers built an AI model that doesn't force a choice between fidelity and realism. The technique is based on a generative framework called conditional flow matching, which you can think of as a process that learns to morph random static into a crystal clear image in a series of smart steps. The secret sauce is how haze matching is guided. At each step of the transformation, the model looks back at the original hazy image. This constant reference to the ground truth acts as a tether, allowing the model to generate a sharp, realistic image without hallucinating details or drifting away from the underlying biological reality. It's like an artist painting a photorealistic portrait while constantly checking the reference photo to ensure a perfect likeness. The team tested haze matching against 7 other methods on 5 different datasets, including both synthetically generated haze and real-world messy microscope data. The results were consistently impressive. While other methods excelled at one metric at the expense of the other, for example, getting a high peak signal-to-noise ratio, a fidelity score, but a poor learned perceptual image patch similarity, a realism score, haze matching achieved a strong, balanced performance across the board. A huge advantage of this method is that it doesn't need to be told exactly how the image became hazy in the first place. This makes it incredibly practical for real labs, where the causes of image degradation are complex and unknown. Furthermore, the model was shown to be well calibrated, meaning it has a good sense of its own uncertainty, making it a more trustworthy tool for scientific analysis. By creating a tool that offers both realism and fidelity, this research isn't just an incremental improvement, it's a step toward democratizing high-end scientific imaging. It raises a fascinating question. If we can use AI to give a cheap microscope the power of a device costing 10 times as much, what other scientific tools are waiting for their AI upgrade? If you enjoyed this breakdown, don't forget to like, comment, and subscribe for more AI research made simple.